The backward direction, however, will be a little bit complicated, because this time we're going to use the fact that alpha is irrational. So alpha will no longer have such explicit form. So what good properties of irrational numbers do you know? One good property we could think of is the fact that multiples of irrational numbers form a dense subset of the circle, modulo the integers. And that is what we're going to use in this backward direction. So, here's a famous fact. That alpha being irrational implies that z times alpha plus z mod z is dense in the circle, which is R mod z. Some of you might have already seen this proof with the real analysis or in some other classes, but I think it doesn't hurt for me just to repeat the proof. The key idea of the proof will be the pigeonhole principle. So this is a proof of the fact for any epsilon greater than 0, you first pick an integer n large enough such that 1 over n is less than epsilon. And you divide the circle to n equal pieces. Say this is your circle, and you're gonna divide this circle into n equal pieces all the way back. Say this point corresponds to 0, 0 plus z. The goal will be to use ma plus n mod z to approximate any number on this circle. And our first step will be to try to approximate 0 plus z on this circle. Namely, we want to find an integer in this arc or this arc. They are both of length epsilon. So we want to find a point here or here, a point here that can be expressed as some integer multiple of alpha plus some integer. Now you consider the sequence. Alpha, 2 alpha, 3 alpha, all the way through n plus 1 alpha. Because there are n plus 1 numbers, and there are n intervals, and those numbers all lie on this circle, mod 1. It follows that there is 2 of them that lie on the same arc in those n arcs. So by Pigeonhole Principle, there exists m alpha mod 1 and n alpha mod 1 such that they both lie in some interval, say k divided by n to k plus 1 divided by n, where k is greater or equal to 0, less than n minus 1, actually less than or equal to n minus 1. And it follows from here that there exists two integers L sub m and L sub n such that the absolute value of m alpha plus L sub m minus n alpha minus L sub n is less than 1 over n. Because they lie in the same interval and you take the subtraction, the difference will be sufficiently small, smaller than 1 over n. So if you remove this modulo 1 from the parentheses, then you have to add some integers to those two parts. So this absolute value is less than 1 over n. And remember, 1 over n is less than epsilon by our choice at the beginning. But at the same time, this is very important, this is strictly greater than 0. Because from beginning, you can always choose m to be not equal to n. Because we are choosing 2 points in this sequence, not just 1 point. So here, m is not equal to n. And if m is not equal to n, the number here must be an irrational number. In particular, it is not equal to 0. So this must be greater than 0. So this part, let's denote this part by beta. And you consider the set 0, beta, 2 beta, and so on. And this set is epsilon dense on the circle T. What do we mean by epsilon dense? That means every point on this circle is within epsilon of some point in this set. So if I pick any point in the circle, there must exist a multiple of beta such that it falls into this interval. And in particular, this point and that multiple of beta has difference less than epsilon. And why is that true? That is because our beta is somewhere in here or here. So if you take the multiple, you will move around this circle and you fall into every arc on this circle of length 1 over n. And 1 over n is less than epsilon. So you can always find an integer such that that integer multiple of beta fall into any given arc. So it can be close to any chosen point on this circle within the distance of epsilon. But the epsilon is arbitrary. So this shows in the end that z times alpha plus z mod z is dense. And this proves this fact. And you probably have seen this proof before. Maybe my argument here is redundant, but just for completeness, let me just add this proof. And now let me move back to the proof of the ergodicity.